Not you. I'm just calming myself. Woosa, woosa, woosa. What is that from? Bad Boys? Bad Boys 2? I feel like there's some like Will Smith, Martin Short movie that did that, but I can't remember which one it was. Something like that. Okay. I have no idea where you dropped off. I'll record something and get it back posted for you guys. Okay. Yeah, so once we have the radius using Newton's laws and thinking about centripetal motion, all physics has stopped. We have now moved into a geometry problem. All right. And if, let's see here. You can almost see it. If theta is really small, then phi is really close to 90. Right? If theta is really small, cosine of a really small number is approximately 1. 1 minus a number close to 1 is really close to 0. And dividing a number by 0 gives you a really, really big number. Inverse tangent of a really big number. You remember what tangent looks like? The tangent function? Yeah, like this. All right. If you plotted tangent as a function of an angle, if you plotted tangent as a function of an angle, it blows up to infinity at 90 degrees. And it comes in from negative infinity and it blows up again. Sorry, that blow up should be somewhere else. It comes in and it blows up again at, let's see, 270 degrees. And it keeps doing that. So this number is really close to 1, which means this number is really close to 0, which means the argument of the entire tangent function is really, really big. Which means if I take the inverse tangent, phi ends up being very close to 90 degrees. Which means alpha ends up being very close to 0. And so that's where I got that idea that theta and alpha are roughly the same. If theta is really small, alpha ends up being very small as well. That relationship doesn't hold if theta gets too large. You know, if you do a half circle in the magnetic field, that relationship will no longer hold. Yeah, okay. Does that get you? I know that's probably more than, does that get you going? Okay, just making sure. Yeah, I mean, I think probably one of the fascinating things, aside from electricity generation, is just the ability to sort things. So this gives you an interesting, I mean, yeah, like mass spec is the canonical example. Oh shoot, we should talk about a velocity filter. Oh, we should do that too. Okay. You already know the bottom line, but I should talk a velocity filter at some point. But probably have it on my notes, but it just rings a bell. I mean, I read my notes thoroughly before I came to class. Other questions? Oh, yeah. Let's see if it'll let me into Moodle here and see if I can change the. Let's see if I can fix this radians. You're saying that problem in particular is yelling at you for radians and radians and degrees, eh? Beam steering. Oh, incidentally, I showed you CERN, right? Last time I was just talking about CERN. That's how they get the charged particles to move in a circle. So that 27-kilometer circle that I showed you that was underground and just kind of drew the outline, how they actually get the charges to move in that circle is that periodically they have magnetic fields at points along the circle to deflect the particle, to keep it moving around in a circle. It's not a continuous magnet. That you know, that would be really, it's just a bunch of really short segments and then it bends, you know, like, so that's how you get a particle accelerator to bend the particles. Let me make sure here. Validation, okay, mathematically equivalent, set that up. And let me make sure that I haven't done something goofy here. So this has rads in it. Coefficient, cosine, okay. I'll double check to make sure I don't want to, I don't see the exact issue off the top of my head here, but I'll double check to make sure. So, all right. Other questions? It should allow you to enter in radians or degrees. So I'm going to go back and double check to make sure. I don't see, it had mathematically equivalent checked. So it should be able to do either or. So I'm going to dig in the code to make sure that I converted everything. So everyone's, just like that blood flow problem, I forgot to convert centimeters to, I forgot to tell the program to convert centimeters to meters. I just want to dig through and make sure that I didn't do something like that on this one as well.
Going up like around 4.8 degrees.
Yeah, I don't see the problem immediately off the top of my head, so I don't want to spend the next 15 minutes trying to hunt it down. So I'll just check it when I get back to the office. But I'll make sure to run a regrade after that. Let's see here. Calculate Q6, check units. Okay. Okay, what else you got? Let's throw this one up here. I don't know if we'll actually work the problem or not, but yeah, this is, I always debate, I mean, maybe I always get stuck because I'm like, I always debate showing you this just because it's really cool application of physics. I just don't necessarily agree with how they're applying it. But on the other hand, I also think about like, well, I mean, you know, nuclear physics is a really cool physics problem. It's just that somebody decided to turn it into some like explosion in the upper atmosphere, which means it's not cool. So, you know, life goes on that, but it's interesting at least. So I'll go ahead and show this, but it's a really interesting application of the magnetic force. So let's see here, I'll turn that off for a second. So let's see here. Let's get this going. Shoot, I forgot to share the screen. I am so sorry. Crap. Everything always goes sideways when the internet drops. So, okay. So now I seem to remember, it's been a while since I watched the clip. I seem to remember the guy being overly enthusiastic about it, which is also just kind of weird. But please be careful. He uses some terms completely wrong, but that's okay. So, oops, no.
The electromagnetic gun is now reality, with the railgun making its public debut at the U.S. Navy's Science and Technology Expo on Wednesday. The railgun uses electromagnetic energy to launch a projectile between two conducting rails. Roger Ellis is the program officer.
It's amazing to think about the science and technology we've developed, that we can be able to concentrate that much electrical energy.
Of course,
create a magnetic force.
Okay, electrical energy, it's the magnetic field, like, okay.
Within 10 minutes.
The railgun fires the projectile faster, farther, and with greater impact than a gun that uses gunpowder. For a 5-inch conventional gun can send a projectile 13 nautical miles, the Navy says the railgun can send it 110 nautical miles. Chief of Naval Research Rear Admiral Matt Winter said he expects the railgun will be on Navy warships in the next decade.
It's like a flux capacitor, right? You're sitting there thinking about these next generation and futuristic ideas. And we've got scientists who have designed these, and it's come to life.
Sea trials beginning in 2016, made possible since researchers reduced the amount of space the gun needs.
We've shrunk that power.
Okay, that's enough. I don't think there's anything else. So, I mean, I always find it fascinating because like those are like 1-inch steel plates. So it's and if you catch it, they said you can accelerate. We could run the problem if we want, but you could accelerate a projectile up to Mach 7 in like 10 milliseconds or something. It's something like that. Okay. Now you have the basic idea of how to get that value. Okay. So what's going on? And I'll give you the setup here. You can kind of see it. Let me see if I can get a cross-sectional view. You can kind of see it here. Here's two rails that are supposed to carry the current, and the projectile actually bridges those two rails. So the current itself actually goes through the projectile, and they showed. Let's see here. Sorry, I'm trying to find the rear end of the projectile that they have. When he was loading it, where is it? Right there. You see that? That's actually the place where it bridges between the two rails and it runs current through the projectile. Okay, the back part of the projectile. Okay. The other thing is you saw all this like flashing, lights or whatever. Please bear in mind, that's not gunpowder, that's actually molten metal. Okay, so like the explosion that you see when it actually launches the projectile, that's actually molten metal from the rails being ejected out the front. Or for example, when it's going through those plates, it's not that that's an explosion from gunpowder or some chemical reaction. No, that's literally this thing is flying so fast that when it hits the metal, it just vaporizes. I guess that's not probably the right word. It just melts it. So not only is it kind of, how do I say? They call it a kinetic projectile. Okay. So it's not the damage doesn't come from the fact that there's an explosion from chemical, like a chemical reaction. It's rather from just the sheer impact. That's kind of interesting. Anyway, let me give you a setup. You actually have all the information you need in order to kind of understand what's going on here. A simplified circuit diagram would simply be what we have over here on the right-hand side. Okay. What you have are two rails. Two conducting rails, really long. You have a battery. Now, usually this battery ends up, I say a battery, but usually I think they might have equipped one on a nuclear power destroyer. So when I say a battery, I mean like, a power plant. Okay. But we can model it as a battery. The projectile's here in blue. And essentially, all you do is you close a switch so that current runs on your rail and through the projectile. That's the basic setup, and you have all of the physics knowledge that you need in order to kind of calculate the rest of this. Okay? Or at least to a rudimentary sense. So let's think about this. First of all, you have current running in a loop. Right? Now it's a square loop, that's okay. First question for you. If current is running counterclockwise in this loop, what's the direction of the magnetic field inside the loop? Which direction is that magnetic field?
Towards you.
Yeah, out. Yeah. Good. You can always take your thumb, run it in the direction of the current. Your fingers will curl in the direction of the magnetic field. And I'll take the bottom wire. When I hit inside that loop, it's going up. And it doesn't matter which wire you use. If you use this one, the current's going this way. The magnetic field is up. Okay. So right here in this region, the magnetic field's out of the board, coming towards you. Good so far? And again, we're just using. Next question. The magnetic field due to these three pieces. So I'm going to take my blue bar as being the system, and I've got magnetic field due to these other three pieces. Okay? What direction is the force on the blue bar due to the magnetic field of the other three? What direction should the force be? Remembering that current's running up through that bar. Don't forget that. Right, there's current current's running in this direction through that bar. So what direction is the force acting on that bar due to the magnetic field of the other three segments? Like, how do I get the direction of the force? Right hand rule. Run your fingers in the direction of the current. Point your palm in the direction of the magnetic field. Your thumb will give you the direction of the force. So if we run our fingers up the direction of the current, we've already argued that the direction of the magnetic field due to the other three wires is out of the board. The force acting on this blue piece will send it down the rail. So you have this the force acting on that blue piece is going to send it down the rail. Say FB. Oops. I think I have something. There we go. And that's also why the rails have to be conducting the full length, is because as this blue piece moves down the rail, you still have to complete the circuit. And where else have I seen? I've seen some proposals. So this is probably the only application I've actually seen that uses it. But some people said, oh yeah, this would be a really effective way of launching things into space. Like, just set up a rail gun, close the switch, and just accelerate this thing all the way out into space. So you could, I mean, theoretically you can do it. From a practical standpoint, it's really hard. And part of, it's funny, one of the strengths of this is also one of its weaknesses. I said, hey, you heat up the rail so much that they literally vaporize as your projectile's traveling down. Usually, if I recall correctly, like reading a couple more articles, it's like you can get right now like 6 or 8 launches, and then you have to actually physically replace the rails inside the mechanism. The rails degrade so much that after about 8 shots or so, you can't actually conduct a current efficiently through the rails. And so you actually have to literally pull the rails out and put new ones in, which doesn't make it very effective. All right. But for a space launch system, for example, okay, you launch your satellite. Okay, yeah, you got to replace your rails, but you're not in a hurry, right? You just drop a new set in and however long it takes. Yeah, so you can do this kind of thing. Do I see that? If you're trying to launch something really quickly, it's not going to work very well. But you could do this. You could build one of these just in your house, just to shoot BB pellets at your friends. Oh, I should have put the jump in. Oh, okay, I'll have to bring that in sometime. I don't know. I mean, I have an exercise of running the numbers, but you basically already see where it goes. I mean, if I want that rail to be at Mach 7, if I want the final speed of the rail to be at Mach 7, you can figure out what the acceleration has to be, right? It said 1/10 of a second, and it said Mach 7. So now you got a time interval and you have a final speed. You can find me the average acceleration. If you know the average acceleration, you can tell me the net force acting on it. If you have the net force acting on it, you can tell me what current has to actually be going through the rails. Unless you want me to do that. I'm seeing no reaction whatsoever. I mean, at some point, and I should say, at some point, like, I hope that you get to the point in physics where you can say, okay, this is the process I have to follow. Do this step, then do this step, then do this step. So yeah, I know I can do it. Now I just have to sit down and actually write down the equation. Like, yes, I'm convinced that will give me the right answer. Okay. That's always good. That's probably, truth be told, that's probably where the most of this physics will come back into your everyday life. I mean, whatever profession you go into, it's going to be, okay, organize the solution in your head, but you don't actually have to do it. right? You say, well, I know the time and the final speed, so I can get the acceleration using the kinematic equations. Okay, got the acceleration. Now I'll use Newton's second law to relate the acceleration to the net force on the object. Okay, I did that. And now I will use the definition of the magnetic force to find the current in the bar. Okay, I got that. Yay, nay? I mean, you see, okay, this is, okay, beating a dead horse, I see. So I won't do that. I mean, you could. From that video, I'm not gonna run through it, we've already kind of outlined the process. But from that video, you could actually pull the mass, they said Mach 7 in 10 milliseconds. Okay? And I think they say somewhere else, or I can't remember if I looked up a spec, but it's about 125 kilogram mass. That projectile, that's about as large as that projectile can get. Now, that's not the one that he was hand loading, right? Like, you ever notice that? Right, like bank heist movies, like The Italian Job, like they pick up a gold bar like it weighs nothing. Like you pick that up, it's like that's like 60 or 70 pounds, dude. Like you should be straining, right? So it's the same thing here, right? Like they say 125 kilogram mass, and that guy just loaded it in. Like no, that's it, right? So yeah, if you look up the spec sheet, it's something like 125 kilogram mass. From the video, it was Mach 7 in 10 milliseconds. And I just went ahead and I just estimated, okay, well, I know the max sustained field that you can do is about 10 Tesla. And you can go through and you can actually figure out how much current actually has to be running through the rails in order to launch, to get these things. And I don't even remember what I got. Correct. I don't remember. I'm sure did I program it in? Oh, good. I got something like 3 times 10 to the 8th amps. Now, literally, I did exactly right. Kinematic equations. That's all I did here, right here. Newton's second law, and set it equal to the magnetic field. Excuse me. Should have some. Yeah. Okay. And so that's all I got down here. Okay. So yeah, something like, even if it's just a 10 kilogram mass, that's 3 times 10 to the 7th amps. That's a lot. Like, I'm pretty sure that we could say that's like, you know, the entire city of Hanover's electrical draw. Like, if you took 10 to the 8th amps, like that could probably power the college for like a week. Like in terms of the electrical consumption. I mean, that's a lot. Which is why you need like a nuclear power plant in order to generate. I mean, I'm not even sure how they do that. Oh, actually, I got an idea. That's really hard to store. That's really hard to just drive that amount of current right away. Okay. So what do?
Store it in solenoid.
Store it not in a solenoid. Oh, I see what you're saying. Yeah, I like the idea. I think my guess is what they have is a capacitor bank. Probably what they do is they draw the charge from their nuclear generator and set it into a bank of capacitors. And then when they want to actually do a shot, they flip in the capacitors into the circuit and it just, that's my guess. Yeah. The other reason you tend not to use solenoids require a lot of copper. Copper is expensive and heavy. So instead of doing it from a magnetic standpoint, you do it from an electrical standpoint. Yeah.
Isn't what we saw on the round exactly opposite of what happened in question 2 on the homework?
I don't know. Was it stopping something?
Well, like it was the direction thing. So wouldn't it go to the left instead of you just explain like why the force goes to the right?
Oh, why the? Oh, okay. I see. Back. Oops. Wrong way. This way. Why the force goes to the right would be that so the current is going in the Z direction. The magnetic field is going in the X direction. So this would be the direction of my fingers. This would be the direction of my palm. And so the force will be direction of your thumb. Yeah, so it would be the right hand rule. So yeah, again, we've got I've set the battery so that the high potential side is on the left. And so that will drive the current counterclockwise through this circuit. Unless I've messed something up. I haven't used my left hand. Okay, no. Okay, good, yeah. Yeah. It's not past me to accidentally use my left hand every once, so I fall for it too. You notice I walk around with my hand in my pocket, right? Like that's forces me to use my left hand. No. Yeah, melted rail coming out the backside. Seems kind of odd that you'd build something that's self-destructing. Okay. Other questions? Okay. Well, I could go into a pet peeve. Could always do a pet peeve instead. Sorry, I'm just looking at something here. Do you want the velocity selector or do we want to do? We're talking about forces. Let's do a velocity selector real fast. This is another pet peeve of Greg's. Not because it's not interesting, but there we go. There, pet peeve of Greg's. Because it just states the obvious, I guess. So you will run into this as well. So I've actually given you one way that you can accelerate charges. In fact, you did it on your first exam. If you remember, I'm sure you did it on your homework too. But one way that you can accelerate charges is that you set up a pair of charged capacitor plates, right? Set up a pair of capacitor plates. I put a high positive charges, negative charges. And what I can do is if I introduce an electron between those capacitor plates, it will accelerate towards the positive plate. Okay. So, and you know, we can find, if I give you enough material, like the charge density, I give you the plate separation, and you can, assuming I gave you the right amount of information, you can figure out what the acceleration of that electron is. If you know. And in fact, you could tell me what the final speed of the electron is. If it starts on one side of the plate and accelerates to the other side, you can tell me what the final speed is when it gets to the other side. I don't think, do I have to, I see people nodding. I don't think I have to convince you on this. So here's an issue though. Say, for example, I don't know what's between my capacitor plates. Say that I don't know if I actually have an electron. For example, what happens if I know that I get some electrons, but maybe other places, maybe I get, I guess sulfur. Maybe I might have some sulfur, which if it's ionized, it has -2. Or maybe I get some chlorine, which ionized, I guess it's -1, et cetera, et cetera. Say I don't know what I actually get between my capacitor plates. Can I say for certain that they have the same speed at the end? No. Why? Why won't all of these objects have the same speed at the end? They have different masses, okay? So the masses will affect the acceleration. What also affects the acceleration? The charge, right? Not only do they have different masses, but even more, they have different charges. And of course, the acceleration that they feel not only depends on the mass, but because I'm using the electric field, it also depends on the charge. right? So this acceleration is going to be a function, it depends on both the mass and the charge, which means my final velocities, who knows? Right? Again, I'm assuming that I don't know what these are. I just have a bunch of charged particles. The fact that they don't have the same charge and the same mass, in fact, it's good to assume, you can't say for certain that they're going to have the same charge and the same mass. It's always good to assume they're not. Right? So where does this come into play? Mass spec. I keep coming back to it because it's just a wonderful tool. In fact, we already talked about it. The radius of the orbit. I should have just written it down. Here. We see that the radius of the orbit, r, is equal to, oh goody, I get, let's see, mv over qb. Right, a v cancels out. So I get m divided by qb. Okay, yeah. So you get something like this. Now, mass spec, you don't know what's going into the machine. Right, that's the whole point. Why do you do mass spec? To figure out what your thing is made out of. Which means you don't know what's going into the machine a priori. In order for mass spec to work, in order for you to make a statement about the charge to mass ratio, what can you tell me about the speed? What do you have to make sure about the speed? You don't know what these things are made out of. Right? If you want to make some quantitative statement about the charge to mass ratio, what do you have to make sure about the speeds? What do you have to do? You have to make sure they're all entering the mass spectrometer with the same speed. Do you see how a capacitor would be an issue here? If you try to accelerate these fragments using a capacitor, they accelerate at different rates, which means you cannot guarantee that they'll all have the same speed at the end. You say, but great, if I knew what they were at the beginning, then I can guarantee they have the same speed at the end. I say, but you don't know what they have at the beginning, right? That's the whole point. You don't know what you're starting with. Do you see the problem here? The question is there a good way for us to figure out this? Is there a way for us to prepare these unknown particles such that they have the same speed at the end? The answer is yes. Then the question becomes how. So the answer is yes, the question is how. And that's what's called a velocity selector. We can set up a way of filtering out particles such that we can say they all have the same speed. And incidentally, it will be, I gotta double check, it will be independent of the charge of the particle. Very important. In fact, it'll be independent of the mass of the particle. Also very important. There is a way to actually set it up so that you get the final speed that's independent of the charge and the mass of the particle. In other words, more advantageous than just using a capacitor plate. Okay. So how do you do this? You already know the answer. So velocity selector. Say for a moment you have some unknown charge. Let's for demonstrative purposes, let's call it positive, but the results can be extended to be generic. Okay. So for the purposes of the discussion, let's say we have a positive charge. We'll go through and discuss everything, and then we'll say, okay, now this applies generically to any charge. Okay. So here's the question. Let's say we have a positive charge entering from the right-hand side. And we expose, which direction do you want the magnetic field? You want it in the board or out of the board? Out, okay. Let's say that we have a magnetic field going out. Okay. And this, I'll use this to refer to the region of space that this is not a parallel plate capacitor. I mean for this to represent the region of space where the magnetic field is present. So maybe I'll just draw it as a box, just to give us some sort of delineation. Question for you. When this particle enters the box, the region of the magnetic field, which direction is it deflected? Down, right? V is going this way, palm is going out, direction of the magnetic field. Particle's deflected down. Good so far? Gets deflected down. That means that you end up with some positive charges on this surface. Right, it gets deflected down. That means you get some excess positive charges on this that surface. Okay. Next question. If I don't want positive charges to hit the bottom surface, right? I mean, one thing I could do is turn off the magnetic field. That's the boring way to do it. If I don't want positive charges to hit this surface, which direction should I apply for an electric field? Muscle memory, sorry. Say I want to apply an electric field to make sure that those positive charges don't hit the bottom. Which direction should that electric field be? Up, right? The charge, when it sees the magnetic field, wants to deflect downwards. Let me apply an electric field going upwards to prevent that from happening. So I'll apply an electric field upwards, and I will do it so that now this charge just goes all the way through undeflected. Quick, what's the net force acting on that charge if it goes through undeflected? 0. Good. Right? If the charge goes through undeflected, that means the acceleration is 0. By Newton's second law, the force is 0. Next question. What forces are actually acting on this charge as it goes through the magnetic field region?
So, the force of the magnetic field minus the force of the electric field.
Good. We had the force of the magnetic field going one way. We had the force of the electric field going the other way. And apparently, when I take those two into account, I should get 0. Quick, what's the definition of the electric force? Don't give me the point charge one. I know some of you are thinking KQ over R squared. That's not the one I want. Yeah. How does the force relate to the magnitude of the electric field? Let's go to it. I'm sorry? Oh, yeah, I love it. I love it. I love it. That relates the electric field to the electric potential. Yeah. If I know the electric field, how do I find the force? I'll write it up on the.
Electric on the bottom of Q or times Q?
Is it? I'm sorry?
Electric field divided by Q.
Times. Yeah. I'll write this as the charge times the magnitude of the electric field. Right, if I know the electric field, I multiply by the charge to find the force acting on that charge. Of course, over here, the force of the magnetic field is given by Q times how fast the charge is moving times my applied magnetic field. That whole thing equals 0. And then we say, oh, goody, goody. What's the goody, goody? The charge, you notice I have the charge for both of those terms. the charge cancels out. Remember I said, is there a way for us to select a speed that's independent of the charge? There's the independence. The electric force depends on the charge, but so does the magnetic force, so I can cancel those out. And I end up with this. If you want to select a specific speed, what you can do is apply a magnetic field, one direction. You can apply an electric field perpendicular to the direction. And by tuning those two values, you can select a speed that you want.
So this only works when both of the fields are in opposite directions.
The force of the two fields are in opposite directions. Yes. And my guess is this solves our problem. Remember, mass spec, for example, requires us to know exactly what the speed of the fragments are before they get into the field, the magnetic field that causes the curves. Well, how do we do that? Well, before it goes into the magnetic field region, let's set up a region where the magnetic field is this way, the electric field is this way, and based on the values that we use for that, it will filter out fragments moving at exactly that speed. So now I know the speed of the fragments when they actually start getting separated. And I think I actually have a picture here. I'll throw that up and then, sorry, I get kind of excited and then I lose track of time. This is just shamelessly stolen from some textbook. So when you're doing mass spec, you've actually got two magnetic fields. You've got a velocity selector so that you know the speed of your fragments before it hits this magnetic field and gets sorted. You stack those two on top of each other. And I don't know, has anybody played with the mass spec stuff?
It's currently being fixed. We have the
Oh, it's currently, okay.
Mass spec is being fixed, but we have the GCMS.
Okay, see, I don't know anything about GC mass. I was gonna ask about the dials that you have to turn, the settings. There's probably one for the accelerating magnetic field or something like that, and then there's probably one for the sorting field, and I'll have to look at it. Yeah, anyway. I'll leave you there, sorry. I'll pick up there on Friday. I'll leave you there. Thank you for your attention. Remind me to end 5 minutes early.